Yeah. So we're going to start this week by looking at the history of the atomic theory, which is, we call it atomic theory because it's constantly being refined and refined. And what we'll see is 100 years ago, we were just developing some early look at the atom beyond just philosophy, and then advancing that into more of a quantum theory. And so it's an ongoing refinement process as we learn more and more about it. And then one of the big things I want us to try and analyze today are Dalton's laws. Dalton's one of the big early theorists about the atom. And one of the things that we'll see is he came up with theory very early, some laws, and then as the more and more experiments were occurring, his laws, some still apply today, and some have been overridden or disproven or not exactly correct based on what we know now. So let's go way back, way back, over 2,000 years ago. Democritus was one of the men of note who did philosophy at the time in regards to the atom. And it wasn't really scientists back then, they were philosophers. Scientists are able to do experiments and test them and go through the full scientific method. And it was hard to do experiments at the time based on the technology available or the lack of it. But he did give the word atomos. His philosophy at the time was not widely accepted. He thought that the atom was this, we were all made of really tiny atoms and they're indivisible. Whereas Aristotle, around the same time, thought that matter was made of the elements, like the movie style elements, air, water, fire, earth, the Wiccan elements, which arguably are more entertaining, but it can all, not the accepted theory anymore. So as you can see, I've got a little graphic on the bottom. As much as I like Avatar: The Last Airbender, we'll keep fiction in fiction. And one of the big things about Aristotle is he thought that matter can be kept broken down, can be continuously broken down into smaller pieces. There's no base unit, whereas Democritus thought that there was this one, eventually get to one particle that's the smallest piece of matter. And then it wasn't until the early 1800s we get John Dalton. And John Dalton really is responsible for some early theories. Oh yeah, sorry, I'll slow down a little bit. If I'm mumbling or anything like that, let me know. I think we'll go back to this page because there's something you can write down. Thanks for letting me know. Have you talked about Aristotle and some of your other classes? I don't know if English gets into any of these old scripture writings, Socrates, Aristotle, Plato. In my classroom, I actually have this little book of Plato where you can read about some of his early philosophies. Okay, so we'll sit on Dalton's page for a little bit. Dalton proposed again that all matter is made of atoms, so kind of a follow-up to Democritus. And the idea that these atoms are indestructible, indivisible, they're the smallest form of matter, eventually get to one particular particle. And in general, now this is a really big idea at the time. In general, Dalton said that atoms cannot be created and they cannot be destroyed. And then he gets into a little bit about rearrangement of atoms and compounds. But these tiny particles, they exist, they can't be destroyed, and they no more can be created, which if you imagine at the time could be felt as pretty controversial. And imagine coming up with these theories with the technology available, the lack of technology available. He starts differentiating between elements and their properties and saying that all atoms of a given element are identical. At this time, the periodic table is starting to be developed by Mendeleev, a name that we'll hear later. And Mendeleev is separating properties or elements by properties and relative mass values, largely studying gases. And so Dalton's saying that, okay, once we've isolated this element, all atoms of that element are identical. Now, you may be hearing some of these and think, okay, like that makes sense, but what we know now, or we maybe learned in 8th grade or biology, I know that's not entirely true. There's some exceptions to that, and that's very good. That's very true. There are some exceptions to what these theories are, but at the time, this is how they were presented. And even more impressive is the idea that Dalton thought that compounds, there are substances that aren't elements. Like water is not an element. Water is a compound that is comprised of hydrogen and oxygen. And it still impresses me how he came up with this theory, again, based on the available information and observation. And really, the idea of chemical change was born as not just an observation like this looks like something happened and we now have something new, but what is happening during that chemical change. And specifically, number 5 is talking about when a chemical reaction happens, it's actually the rearrangement of these elemental particles, like puzzle pieces, breaking and reforming. And that's the idea of a chemical reaction. So some of the main laws and theories that we still use today that are very important are the law of conservation of mass. And these are called laws because we base theories off of these laws. We say that these laws are true and we're going to base all our other theories off of these laws. So the law of conservation of mass, matter cannot be created nor destroyed. It may change form, but it isn't just completely destroyed. It doesn't disappear. Nothing disappears and nothing is created out of nowhere. The law of constant composition, otherwise known as definite proportions. If you have a given compound, the relative number of atoms are constant, meaning if you have a water molecule and then you have a second water molecule, those 2 water molecules should be exactly the same in regards to 1 oxygen and 2 hydrogen and the way that they're bonded. Otherwise, it's not water, it's something else. So all water molecules are identical, is essentially what this is saying. Now, there are some slight exceptions with mass and number of neutrons, but chemically and properties-wise, looking at physical properties and chemical properties, all water molecules share the same physical and chemical properties. And then law of multiple proportions. When 2 or more elements combine, there are more than one way that they can form compounds. For example, and this, I think I kind of didn't wordsmith that well enough. When you have 2 elements, there are more than one way that they can combine, and those different compounds have completely different properties. Meaning, let me jump to the whiteboard really quick. Let's take nitrogen and oxygen, for example. These 2 elements can form a wide variety of compounds. You can have 1 nitrogen and oxygen. You can have 2 nitrogens and 4 oxygens. You can have a nitrogen with 3 oxygens. You can have a nitrogen with 3 oxygens with an extra electron. We'll talk about charges at some point. These are all perfectly viable compounds that exist naturally. So nitrogen and oxygen, there are more than one way that they can combine, and each of these have different names, completely different properties. And so that's the idea of multiple proportions. Imagine what we can do with hydrogen and oxygen. We know that water exists. That's one of the compounds, but hydrogen and oxygen can exist as just one of each, and it'll have a charge on it. You can have 3 hydrogens and an oxygen, it'll have a positive charge. You can have H2O2, this is hydrogen peroxide, which has completely different properties than water. Water we drink, hydrogen peroxide, if you drink, you're gonna die, or if you drink too much of it. So that's the idea of multiple proportions. So notice the year jump, early 1800s and almost 100 years later, late 1800s. This is where electricity really started making its presence as a modern commodity. And just imagine going from no electricity to having a world filled with electricity. What an enormous change. One of the major discoveries in human history. And so in late 1800s, J.J. Thomson discovered the electron. And so the electron is a charged particle. And now, around this time, there was a lot of work in electricity and magnetism, and developed an instrument called a cathode ray tube that allowed him to pass charged particles through a tube and bend as a response to a magnetic field. So if you pass an electron through a magnetic field, it should bend towards the opposite charge because opposite charges attract. And you don't need to know numerically what the charge per gram ratio is, but just the idea that if you have a gram of electrons, he was able to measure the charge of that electron. Now, electrons are ridiculously small. They have a very small mass. So that is a huge charge considering you have a 1 gram of electrons. 1 gram of electrons is enormous. There was a picture, there it is. I kind of did these. Oh, so Thomson devised a model for the atom. And this is where you start finding that the atom isn't the smallest thing. The atom's actually made up of smaller things, and we'll call them subatomic particles. So if the electron is a part of the atom, and atoms are inherently neutral, then the electrons must have a counterpart, protons. So with all the magnetism experiments going on, they were able to detect protons and electrons. And so an early model for the atom called the plum pudding model believed that protons and electrons just kind of float around in this spherical shape. And that simulation that I'm going to have you look at as you experience what would happen if a plum pudding model is correct versus the more advanced nuclear model. Here's an example of a cathode ray tube. Funny enough, early televisions were called cathode ray tubes because the image projected on a television was a result of electrons being bombarded on the screen from the inside of the big box. I don't know if you remember televisions with a huge box. Those are electron propelling devices instead of plasma TVs. Plasma TVs are different, but they used to have this huge boxy televisions that are electron delivery system, essentially, a cathode ray tube. And you can see the magnetic field where a charged particle will deflect towards the magnetic field. And he did some calculations based on how fast it deflected, the angle at which it deflected. And that's eventually how they came up with the mass of the single electron. Millikan did an oil drop experiment. We don't really need to know the nature of the experiment, but there's some old images that I dug up. Just take a look at this number. The mass of a single electron, 9 times 10 to the negative 28. So put 28 zeros in front of that and put a decimal in front of it. That is ridiculously small. So when I say that the electron weighs essentially nothing, compared to everything else we deal with in this class, like protons and neutrons, they have a lot of mass compared to the electron, which is ridiculously small. X-rays are also being developed around this time, so study with radiation and how to maintain good facial hair, which I appreciate from this picture. This is the birth of the hipster hair. There's an old ad for shoe fitting. You might recognize the brand, Dr. Scholl's. They would size your foot by taking X-rays of your feet. We eventually found out that if you X-ray yourself too much, it causes harm. That's why when you go to the dentist's office or the doctor's office and they're taking X-rays, they put this lead vest on you and the doctor walks out of the room because you don't want to get X-rays too much. Becquerel, one of the big names in radiation at the time, one of the ways they measure radiation is by measuring becquerels, which is like a unit of measurement, as if like, imagine we measure meters because someone's name was meter. Not necessarily true for that, but for becquerels, they measure like radiation units in becquerels. He was an engineer, studied uranium. And they wanted to put uranium in road marks, road signs. You know, whoever developed those reflective discs that go on the roads, imagine selling those for 10 cents a pop and how many of those there are. You make a killing. I think the ones that they do up on Highway 80, where they divot them into the roads so the snowplows don't cut them off, those road signs, they're like $10 each, and there's a ton of them. But they wanted to use radioactive material to make these road signs because magically this object glows without any input. They figured out that radiation, however, is harmful, so we didn't want to irradiate all our roads. Radiation had this really interesting effect. You have this object, and it magically gives off energy. And how do you detect that? Well, you have photo paper. Remember we have some image of how they develop photographs. If we were taking photography at school, maybe you took photography last year where you go to the dark room and develop photo paper. I don't know if he still does that. Murat still has you do that. But imagine sticking this rock in the room, coming back the next day, and all your photography, all your paper is developed magically and ruined essentially. And they figured out that this object is giving off radiation, giving off energy. And Marie Curie is arguably one of the more famous scientists at the time for radiation. And there's actually a television series on Hulu, I think, or HBO or something, called Radioactive, based on Marie Curie's life. And I haven't watched it though, I need to. Marie Curie is the first woman to earn 2 Nobel Prizes, one in physics and one in chemistry. And she came up with the word radioactivity. Her lab materials, her notebooks are still radioactive to this day, and they're contained in lead, essentially. But she contracted radiation poisoning and died as a result, as did a lot of people that worked in radiation at the time. Then we get to Rutherford. Rutherford is another big name. So we have Dalton and Rutherford. Those are 2 big names. Thomson's a pretty decent name, but he came up with the plum pudding model. We don't use the plum pudding model. Rutherford really, with his work, refined the model of the atom. He worked with radiation. At the end of the year, we'll come back to radioactivity, and we'll talk about the alpha, beta, and gamma particles. We will get into nuclear bombs and all that stuff. I leave that fun stuff for towards the end of the year. But just a little preview of the different types of particles. Yeah, I can go back a slide. We don't need to know a whole lot about the alpha, beta, gamma particles right now, but this is a reference I'll show you in a second. That slide. So radioactivity, in a sense, just to give you a very brief understanding of radioactivity, is when the atom is unstable. And that's largely due to an uneven or a disproportionate number of protons to neutrons. Inside the nucleus, there's protons and neutrons. And when that quantity is unstable, the atom naturally undergoes a process to stabilize the nucleus. And that largely involves shooting off particles or energy. So alpha particles are the largest radioactive decay pattern, where they shoot off 2 protons and 2 neutrons in this little nucleus, kind of like a buckshot. Imagine like World War I, where they have the little musket guns. Or sorry, not World War I, the Revolutionary War. Little musket shots. There's like an alpha particle. Beta particles are very small. It's like an electron-like particle being shot off. And then gamma rays, gamma is just pure energy. And gamma is the most permeable of radiation. Gamma rays, it is not considered matter. So we talked a little bit about matter has to have mass and take up space. Gamma radiation is not considered matter. It's pure energy. And this can permeate through several feet of lead and you're getting there right now through the window. And if you just have a high exposure to gamma radiation, it starts messing up your cells and DNA and mutates your body, and not the fun kind of mutation. This is like the cancer stuff. So Rutherford, let's see. He worked with an experiment called the gold foil experiment. Thought that he found neutrons as well, but he was largely focused on determining the presence of a nucleus. The idea that instead of this mesh of positive negative charge, this plum pudding model, that's not what it is. In fact, most of the mass is contained in this tiny space in the middle called a nucleus. This is a visual of his experimental design, just a graphic of it. If this works, if this experiment works, what happens was he shot alpha particles, these protons and neutrons, he shot them at a piece of gold foil. And if the plum pudding model was correct, then all of the alpha particles should just pass right through. But what happened is a small percentage of them deflected. And you can see these deflections off in random directions. The zinc fluoride screen just gets little blips to show that they're being detected. And so because some of them were deflected, whatever deflected them, a part of the gold, whatever deflected them needed to be very small and dense, because only a small number of them got deflected, and should have a positive charge. Because these alpha particles are positively charged and the nucleus is positively charged, when it comes into contact, the positive charges repel each other. So we now have some generic properties of the nucleus. Here is a comparison, and this is the Rutherford scattering simulation that I'm going to have you access for part of your assignment tonight. We'll have you play around with this kind of model, both of these models, and you'll get to see the scattering effect. It's pretty cool. I'll show you what that simulation looks like before we leave. And here's some conclusions. Nucleus is positive, small, and has most of the mass. Let me write that out. Small, dense, most of mass of atom, and should be positive charge, positively charged. Rutherford thought that the neutron, there's something there besides just the proton in the nucleus. If the nucleus was just protons and there's a lot of these positively charged particles in the nucleus, then they'd naturally repel each other. And we don't see that happening with the nucleus. So there has to be something else in there to hold the nucleus together. So he just wasn't able to detect it. When you have a positive charged particle, a negative charged particle, these particles are easy to detect because they respond to magnetic fields. But when the neutron has zero charge, at the time the technology wasn't able to detect it. So often is the case in science where you think something should exist, it fills this gap in your theory, you just can't find it yet, and it becomes someone else's job later to devise a new experiment and discover it. There are a lot of gaps in the periodic table for elements that should exist that just haven't been discovered. And even with the last couple decades, we're still adding to the periodic table as we're synthesizing more and more elements. All the heavy elements now are all artificial though. So following Rutherford and the idea of a nucleus and then electrons existing outside of the nucleus, Bohr comes up with the early basic atomic model. And this is probably the one that you saw in middle school where you're, okay, carbon has 6 electrons, where do they go? 2 on this circle, 4 on this circle, and you just draw them in. This is the solar model. This is not the more current model, but it's the easiest representation of the atom that we look at. So we'll look at the Bohr model a little bit this week. I'm not going to sit on it too long. It's good. It's very good for some concepts, but as far as the details about what electrons are doing, it's not the best. It works for hydrogen, but not other elements. So maybe you're familiar with this circle model. Shows basically electrons exist outside the nucleus in very specific orbitals, is where the word kind of comes from, orbitals. We don't use the word orbital too much anymore, but I will use it for some of the discussion. The better term for where electrons are is they exist in energy levels. And the quantum mechanics behind this theory, I'm not going to get too crazy into it, but instead of having circular orbits, they're actually different shaped orbits. And here's some example of a bubble model of where electrons exist. I don't want to get into too much, but quantum mechanics is developed in the 1920s. And as a result of quantum mechanics and their calculations that quantum mechanics allows us to do, comes all advanced electronics. Your phone, your computer, what we're doing right now, all works because of quantum mechanics. And so the equations allows us to predict with great certainty the behavior of elements and electrons. And electronics are functioning based on this on-off switch. Silicon is a semiconductor, so it has the ones and the zeros of binary code. 1 is on, 0 is off. And so basically what electricity is doing when it goes through your motherboard is it goes back and forth between on, off, on, off, on, off, on, off. And that's binary code. Quantum mechanics helps us predict that behavior, and we use it to do all modern computing, including phones, calculators, cameras, computers, everything. Digital signs, marquees, all that is because of quantum mechanics. Chadwick discovered neutrons 11 years after they were theorized by Rutherford, gets a Nobel Prize for it. And now we're starting to get to the realm where Dalton's initial laws are being disproven, where the atom is not the smallest form of matter. There are things that are smaller than the atom called subatomic particles. And some of these subatomic particles, like the proton and neutron, actually get broken up into even smaller pieces. The proton and neutron are made of quarks, if you've heard of the word quark. And then a word that we'll get into more this week and next week is the word isotope. The idea that you can have two atoms of the same element, but may have different number of neutrons. It could still be the same element, have the same chemical reactivity, and everything's identical except the number of neutrons. And so this word isotope will just sit on for a little bit. You don't have to get too crazy with the word isotope yet. In the 1930s, we start splitting atoms and releases a ton of energy. You can imagine where this is going. By the 1940s, they're harnessed into deadly weapons. But again, the idea that you can split atoms starts disproving Dalton's laws. Dalton said that atoms can't be divided. This is the smallest form of matter, indivisible. These words don't apply anymore to atoms. They can be separated. They can be broken up. Our class is largely concerned with what the electrons are doing. But at the end of the year, when we get back to nuclear chemistry, we'll talk more about nuclear reactions where the nucleus is breaking down and protons and neutrons are separating. But for the vast majority of the class, we're going to keep the nucleus there and not really mess with it too much and just talk about electron behavior, because that's what chemical reactions are, is rearrangement of electrons. So to help us visualize some of these theories, one of the simulations that I want you to take a look at next is the Rutherford scattering, which I'm going to pull up right here. If you go to this is an HTML link, so you should be able to access it as if it's just a website. Go to Rutherford scattering, and it looks like this. You can analyze the experiment from the effect of the plum pudding atom or the Rutherford atom. So I fully encourage you to experiment with both. I'm not going to give you too much guidance on what kind of answers you're getting out of this. I want you to pretend like you're the person doing the experiment, and based on your observations, what kind of conclusions can you come up with? And just to show you how this works, you click this button and it starts shooting alpha particles, and these are protons and neutrons, and you can increase the flow. It shows there are traces, so there's a couple buttons you can click essentially. And at the very bottom, you can see these home button and the Rutherford atom button. If you just want to click over to the Rutherford atom, there's a little tile at the bottom to switch back and forth. So if Rutherford's atom with the nucleus is the true theory, then you can click this button and see what happens when alpha particles get close to the nucleus. And so part of your assignment is to look at the Rutherford atom versus the plum pudding atom and justify why the Rutherford atom is a more correct model than the plum pudding atom. So that is emphasized in your assignment, which looks like this. So compare and contrast Democritus and Aristotle, which was the first couple slides of the PowerPoint. What are Dalton's 5 theories? So just listing them. Then you get into some how and describe questions. How did Thomson's experiment work? This is leading to work with the atom. So this has to do with the cathode ray tube. Describe the plum pudding model from the simulation and from some of the visuals. And then what were the results of the gold foil experiment? Some of that information is in the PowerPoint. And then from the PhET simulation, number 6 is where you're directly responding to some observations made while looking at the simulation. So this is where you want to actually open the simulation and mess around for a few minutes. What evidence suggests the presence of the neutron? I talked a little bit about charged particles, and if the nucleus is just a ton of protons and they're all positively charged, they would repel each other and the nucleus would break down. So there has to be something else holding the atom together, holding the nucleus together. And so there's a little bit about that to help suggest the presence of the neutron. This is why they theorized that the neutron was there before they actually discovered it. And then in the slides, there are specific moments where I mentioned that Dalton's laws were now disproven. How did discovery of the neutron disprove Dalton's laws? So you're kind of synthesizing your own response based on the information that I presented as well.